Hi everyone, this is Keshav Peswani and I'm back with yet another interesting topic in the database learning series, which is MongoDB. MongoDB, as we know, it's a leading NoSql database and it offers flexible and scalable solution for modern applications. But how does it work under the hood? In this talk, we'll delve into the core concepts of MongoDB's architecture, the similarities it has with the SQL database, the data model, what is the collection and what are the documents, how the indexes work in the MongoDB, along with the sharding techniques. This will provide you a clear understanding of its key components and functionalities. Along with it, we'll also see how MongoDB stores the data. So let's start with MongoDB. MongoDB was launched in 2009 as a completely new class of general purpose database, and it quickly established itself as one of the most popular databases among developers. MongoDB retains the best aspects of relational and NoSQL databases while providing a technology foundation that enables organizations to meet the demands of modern applications. Every database, to me, follows a similar pattern or the structure. Let's take the example of SQL. SQL, as we know, it has, from the client's perspective, a SQL query and a data model which consists of tables and columns, and then it has its own backend infrastructure which includes of storage engine, the indexes, the sharding techniques, and the transactions and journaling. Similarly, MongoDB also has its API, which is the MQL, which is Mongo Query Language. It has its data model, which is the collections and documents. It has its storage engine, which started from maps or memory maps, went to wired tiger, and then to clustered collections. It has indexes functionality. It provides you sharding because it's a NoSQL database, so the data is sharded across multiple nodes. And it also gives you distributed transactions, and it has journaling, or what we say write ahead logs. And we'll see how these things are there in a bit more detail as we further drill down into the lecture. Let's start with the data model, which comprises of collections and documents in the MongoDB world. So collections and documents, they're equivalent to tables and columns in the SQL world. So collections is equivalent to the tables, and document are equal to the rows of table. And each key in the document is equivalent to the column. The data in the MongoDB is stored in the JSON format initially, and now it's converted to the binary JSON or BSON as what we say, and this is more efficient in terms of querying, storage, and human readability. So it gives a striking balance between the performance and the human readable data representation. This is most important thing. We also have something called the ID field. It is similar to the primary key in the SQL world. The primary key in the SQL world is the key whose against the entire row is stored in the storage engine. Similarly, in the MongoDB world, we have the ID field, which stores the entire document. If you don't give this ID field, it is automatically generated. It is an auto-generated thing, and MongoDB generates it, and then the document that you have given for storage is stored against it. My JSON consists of key as a name and colon Keshav, and organization as Expedia Group. Then there would be an ID created, let's say some unique ID 1 2 3 4 5 6, and along which this document is stored. So this is the ID field or the primary key concept of the MongoDB. Let's start with the transactions in the MongoDB world. In MongoDB, an operation on a single document is atomic, which means that two different operations cannot update the same document simultaneously. This helps in maintaining the atomicity for that document. And that is the reason that people try to use embedded documents and arrays to capture relationships between the data in a single document structure instead of normalizing it across multiple documents and collections, which essentially translates to that in the SQL world, generally we keep the data in a normalized format, like there would be two tables and one table would be referring to the other table. But in the MongoDB world, it is more advisable that you have a document, and if you want to keep this part of the data, you keep it in the embedded column or embedded data structure. This will give you the atomicity out of the box. But there are scenarios that require atomicity across the documents, and these documents can also reside across various collections. So in order to do that, MongoDB supports distributed transactions. In distributed transactions, the transactions can be used across multiple operations, collections, databases, documents, and shards. And we'll see what shards are, but for now, you can do transactions as you can do it in SQL world. But then there are some catches around it. Also, there are certain properties around the transactions in the MongoDB world. Let's see them and try to understand those properties. So the distributed transactions in the MongoDB, as we know that they are atomic, which means that either all data changes are applied or they are rolled back. Committed transactions make these data changes available to the outside world, which means once a transaction is committed, it is available for the readers to read it. But there is a catch. The read operations for that particular committed transaction may not be visible across all the shards. So when I say that I am doing a transaction, let's say TX transaction 1, and there's something called write concern and read concern. So if the write concern is 1 and the data is replicated across the 3 shards, and the read concern is either 1 or local or majority, then in case of the local or the majority, it may happen the data is not replicated across the 2 remaining shards and the read happens from that 2 shards. That is the reason that read operations, sometimes you still cannot get the latest committed data because of this kind of a scenario. This is generally done to make the transaction speed faster. But if you do a write concern of majority, then it is committed across the majority of the shards. But in case the read is still through local, let's say there are 3 shards and you do majority, the majority would be 2, and the read happens still from the remaining shard till the time it's replicated. Again, the latest data may not be visible for that particular read operation. But it is not true for the aborted transactions case. In the aborted transaction, all the changes that need to be discarded are discarded without being visible. So, aborted transactions are very different than the committed transactions in the case of transactions properties in the MongoDB. The transaction level read preference is set at the start and defaults to the session level or the client level if it's unset at the session level. The read level concerns, as we saw, it includes majorly the local or majority or the snapshot ones. The transactions use transaction level write concern for committing write operations. So there are either this is the write concern or the read concerns, and that is both of these things are needed to read a transaction or to write a transaction. Again, as in the case of the read world, the write transaction concern defaults to session level or the client level if it's unset. So it's always first session and then the client level, both in case of read or write. And supported value in the write world is the 1 or majority. There is no local concern over here in the write world. So this was all about the transactions or the distributed transactions in the MongoDB world. Now let's see what are the indexes in the MongoDB and how they help us. The indexes support the efficient execution of queries in the MongoDB. Without indexes, MongoDB actually performs the entire collection scan. That is, it scans every document and selects those documents that match the query statement. But in case if there is an index that exists for that particular query parameters, and when I say query parameters, take it as similar to the where clause of the SQL world, the MongoDB can actually use an index to limit the number of documents that it needs to find. And how it does it, we'll see now. So MongoDB actually uses something called a B-tree data structure to create the indexes at a collection level. The B-tree data structure is a self-balancing tree which has all the leaf nodes at the same level. This ensures that the worst case complexity of any search that's going to happen will always be a log of n. However, the index stores the value of a specified field or set of fields ordered by the value of that field. The ordering of the index entries in the B-tree data structure, it supports efficient equality matches and the range-based query operations. In addition, the B-tree data structure also helps in returning the sorted results by using ordering in that index. So basically, let's say if I have an index of the range value from 0 to 10, now in the B-tree data structure, it would be ranged out to 0 to 5 and then 6 to 10. Now, if a query comes that I need to find something like less than 5, so my B-tree would help me to traverse from the root node to this one, and I would know all the documents that would reside under or are less than the value 5, because the B-tree data structure would give me that ordering thing, and this will help me in supporting the less than or greater than equal to queries in the login operation. In this case, it supports, or this helps me in limiting the number of documents that I have to go through rather than going through all the documents. And the read performance of the query increases significantly. However, there is a negative impact as well. Whenever there is an update that happens to the document, the index also needs to be updated. So if there are multiple indexes to a collection, then all indexes need to be updated as well, which decreases the write performance of DB. So whenever there is a heavy write to read ratio, the expense is more of index writes, and this will lead to significant increase in the time to write that particular document or update that document. Also, these indexes are actually kept in memory. So when you have a lot of indexes and they are kept in memory, then memory requirement also shoots up. And if that happens, the MongoDB's read performance would also decrease. So you have to be very cognizant of the fact that you have enough number of resources to actually support multiple indexes. There are various types of indexes in MongoDB, the primary ones being the single field index and the compound index. The single field index, it's more of a single field used as an index, and it can be sorted in the ascending or the descending order, whereas in the compound index, it's more of a user defined compound key, and you also need to provide a sort order that tells Mongo how to keep the index. This sort order is nothing but comparable to the comparator in Java world. Then there are other indexes that we also use in the MongoDB world, such as the geospatial indexes, which allows you to store the coordinates or the location data in the MongoDB, and the text search indexes. This is generally supported by the Atlas or the MongoDB hosted on the Atlas world. This type of an index is a sparse index, and it helps in searching the string content in a collection. Then there are hash indexes to support hash-based sharding. This type of an index hashes the value of the field. The advantage is that this kind of an index gives you more random distribution of values along with their range, but it only supports the equality matches and cannot support the range-based queries as what single field and the compound index does. I would like to stop here and give a pause. In the next video, we'll continue with the sharding technique and the storage engine of the MongoDB. We'll also see the verdict when to use the MongoDB and how to use this. See you soon in the next lecture. Happy learning.